So we want to look at applications of forced motion. So what do we want to do? Well, we want to stick to what we said before. So if I look at Newton's second law, I could either write it as the acceleration is equal to the net force divided by the mass, or I could use F net is mass times acceleration. You're going to find out that our focus is going to be on this form right here. I could write it the other one. I think this one's easier to comprehend. So what I want to do here is that I want to rewrite Newton's second law into something that we've talked about in the past. So I'm going to say, now let's remember that acceleration is the change in velocity. And what we mean by that is we wrote the acceleration is the change in velocity divided by the time. And that's what we did in chapter 1. Now, what I want to do with this is that I want to rewrite into L. So if I rewrite into L, it says this. It says that the net force is mass times acceleration, or I can write this as mass, the change in velocity over change in time, and I'm going to say, okay, this is the form of the net force that I'm going to write right here. This is how I'm going to write it. Now, let's look at the situation. It turns out that in most applications, that the change in velocity is always the same. And what I mean by that is that when I look at an object, its change in velocity for various situations will be velocity equal to a constant. So the change in velocity will be a constant. And I will show you multiple situations like this. So it's always a constant. This means when we accelerate, it's the time interval that plays the major role. And so what we'll say here is that what I mean by that is that there are short times and that means here that now I'm going to have a little tiny time. Or long time intervals. And this one means that it's nice and big. So what do I mean by this? So when I look at the acceleration, we can have small or large accelerations this way. So if I have a velocity that does not change, so in other words, this delta V is going to be the same as this delta V. Okay, so the only thing that changes most of the time is going to be what? It's going to be the size of the time interval. So for example, if I have a short little tiny time interval, right? So this is a short time interval. That means I'm going to have a high acceleration. So this will give you a large acceleration. However, if I have a long time interval, a long time, I'm going to have a tiny acceleration. So this will be a small acceleration. So now if I put this all together into Newton's law, we can say here, what does N2L tell us for these situations? Well, it goes like this here. If I have a net force, I can write this as mass times acceleration like this. So then what that means here is that if I look at this situation, I have a mass. And in each of these situations, you could see I have the same mass, I have the same change in velocity. They're exactly the same. So what happens here? This is what happens. If I have a tiny time interval, I get a huge acceleration. And if I get a huge acceleration, I get a large net force. So what happens? I feel a very large force. On the other hand, if I have a long time interval, then my acceleration is small. And if my acceleration is small, then that means that my net force is then going to be small. So what do? I feel a very small force acting on me. So Newton's second law tells us that this must be the case. Right? It must be the case here. And that's what we want to do. We want to study these situations. And so what I'm going to do here is I'm going to give you a silly example. But one that I think is a good example. And it goes something like this. Once we see this example, you'll see that there's lots of examples that we could think about. So let's think about examples. Let's say that this is our first one. Now, suppose that you're driving a big truck and the brakes go out. So suppose you are driving a large, a large truck, and the brakes go out. That means you can't apply them anymore. Now here's the silly question. Is it better to hit a haystack or a pile of hay versus a brick wall? Of course, you would rather hit a haystack. So let's draw this out. Let's see what we mean by this. So what I mean by this is that let's draw two trucks. So I have a truck here. And what we're going to do here is that I'm going to copy this truck twice. And you could imagine that we have the following scenario. I have a truck that's driving very fast. Right, so as it's driving, you're seeing it's going very fast and it's moving at some high velocity like this. So let me copy that. And so let's say that this truck here, let's make it a blue truck. Right, so I have a blue truck and it's driving fast. Now, this truck is going to do what? It's going to hit a pile of hay. So we know that this one's going to hit a haystack. Then I have a different colored truck, exact same truck, but this one's, let's give it a different color. Let's say that this color is violet. Now, this one, on the other hand, is going to do what? It's actually going to hit a brick wall. So when I look here, I can see that there are bricks in this wall. And of course, all these bricks, it's a red brick wall. Right, so I'm looking at this guy and I'm going like, uh-oh, this guy's hitting a brick wall. So when I think about this brick wall, I mean, of course, you would be an idiot to hit the brick wall. If you choose a brick wall, you're going like, oh gosh, give me a break here. Now, what's important here? What's important here is that what's going to happen here is that these trucks have the same speed. Now, one of the things that I said up here is I said that the change in velocity is always a constant. So what we're going to see here is that the haystack and brick wall will stop each truck. So that means here is that their final speeds are 0. Which then tells us here is that the change in velocity between the blue truck and the purple truck is the same. So the change in velocity is not the big part of this issue here. So now let's draw the pictures here. So what's going to happen? You're going to stop the truck. So that means here is that when it hits the hay pile, there's enough hay in the haystack to stop the truck. So then picture-wise, what do I see here? Well, I'm going to see a big mess, right? I'm going to see a big mess. So when I look at the truck is now not moving. We know that it's at rest. Right? We know that it's at rest. But what happens here is that now we got hay everywhere, right? We got hay all over the place. So the hay stops the truck here. So that means here, as we said already, the haystack stops the truck. And then if I look at this, the violet truck here, well, there is the brick wall. And you could imagine that if it slams into the wall, of course, has to be dented here, right? I mean, you're seeing here that as these walls get dented by the truck slamming, what happens to the truck? Well, what happens to the truck here is that it's probably going to look like an accordion. And so as you're looking at this violet truck, it's a violent situation where you're really, stopping that thing instantly here. So again, the final speed of that truck is 0, and that's because the brick wall stops the truck. So the question is, what does physics have to say about this? So I'm actually going to move this over here to try to conserve more space. Okay. So what does physics say about this? Well, let's look at each of these things. So if I apply Newton's second law to this, so if the blue truck hits the haystack, what happens? Well, it takes longer to stop the truck. In other words, this is what we say here. We say that now we have a big time. And what we call this is we call this a long contact time. So what does that contact time tell us? Well, if I have a long contact time, then we know, according to Newton's second law, that this thing must be like this. If I have a long contact time, I must have a small acceleration. So therefore, the net force that they feel is going to be what? We say that they feel less. They feel less because the long contact time tells you that you have a small acceleration. Maybe I should have written this. You have a small acceleration, which then you have a small net force, or you feel less. Now, if I continue to move on here, I could say, what about the purple truck? Well, when I look at the purple truck, hits the brick wall. So that it takes what? Shorter to stop the truck. What does that mean? Well, we know that in this case, we have a tiny contact time. In other words, we have a short contact time. So again, according to Newton's laws, it tells us what? Well, it tells us that I have this little tiny contact time, which then gives us what? A large acceleration. And because of the large acceleration, we then feel a huge net force. So we say here is that you feel more, not less. So if I was to, because a lot of times people make mistakes here and not drawing the whole picture, I want to do a flow chart. I want to do a flow chart of thinking. So the flow chart starts off with what? Well, the first thing you got to do here is that you got to look at the contact time. So from the contact time, you got to tell me about what? The acceleration. And from the acceleration, you then talk about the net force. A lot of times people will only give me the contact time. So you know what I do? I give you a third of the points. If you talk about the contact time and the acceleration, I give you 2/3 of the point. But if you talk about the contact time, the acceleration, and the net force, I give you all of the points.